Welcome to Lecture 2 of the Planets. Today we're going to explore the solar system for the first time, learn something about the distances between the sun and the planets, and we're going to learn something about the size, the actually ginormous size of the solar system and the size of the planets relative to them. I'm going to start with a little review of some of the logistics of the course. Some of you weren't here last time. I'll go quickly. Textbook. Many of you have already purchased the textbook, I know. The Cosmic Perspective. It should be edition 7, the 7th edition, but in the bookstore on the front of it, it says 2nd edition. It's because we have a special cut of this textbook. You'll get an access code for Mastering Astronomy. Many of you have already done this. You've logged on to Mastering Astronomy. I see that over 200 people now have already gotten on to Mastering Astronomy. That's great. If you haven't done so, you definitely need to get your access code and log on to Mastering Astronomy with both the course ID and the personal ID that you get. The course ID, remember, is Marcy67636. A few people emailed me and said they had trouble logging on. In all cases, it was because you didn't use the right website. It's understandable. The right website is pearsonmastering.com. So if you are still one of those people having trouble, pearsonmastering.com gets you on. There's the course ID, then you just need your own homegrown ID. Homework in this course, as you know, will be due every Friday at 6 p.m. It's all online. If you happen to find yourself in Saskatchewan or Nepal, you can still do your homework. Turn it in on time. Fridays at 6. The first homework of the semester is due this Friday, September 5th. It's on chapters 1 and 2. You can find them there. A few people, by the way, have already attempted to do the homework. So if you haven't done the homework yet, you're way behind. You should read chapters 1 and 2. All I can tell you is much of the rest of the semester in this course is introduced in chapters 1 and 2. So you're doing yourself a huge favor by sitting down, finding a quiet chair away from the texting and the emails and whatever other distractions you might have. Maybe friends talking to you, maybe it's a television, maybe it's the refrigerator. Get away from all that stuff and try to find a nice, quiet place that you can go for maybe 2.5 or 3 hours, have a good time, and read the first 2 chapters. They're really pleasant reading. You'll remember what you've read for the rest of your life about our solar system, the sun, the planets, our Earth, and so on. So by all means read, and then go ahead and try the homework. And to remind you, when you do the homework, it's all online, so you can get help. You can actually get hints as you do the homework. Hints cost you a pretty penny. You lose 5% if you get the wrong try, and if you want a hint, it's 3%. So it's actually kind of fun to try the homework out. What I like to do is I read the 2 chapters. I spend a few hours doing that. Then I go and try to do the homework, and when I come to a particular problem in the homework, and if I don't know the answer, I go back into the chapter, I flip through the pages, I find the section that deals with that homework problem, and I read that page again, maybe with an eye toward that homework problem, and then I go back to the homework problem, read it again. For me, it often takes me a few tries reading the problem to really understand what they want, and then sometimes I have to go back to the chapter, the page or two that describes that issue, And then having read it, I go back to the homework problem, and now it makes a little more sense. And so that way you can go from homework problem to reading, back to homework problem, and try to make it all work. Okay, homework due this Friday at 6. I'll remind you that if you haven't signed up yet, you can sign up in any one of these 3 lectures. Almost all of you have already signed up. There are empty seats in this room, so if you're not signed up and or you're on the waiting list, you can get in with no trouble. My office hours are Tuesday at 1 and Wednesday at 9. So you can get on there, get in touch with me. I'm in the Hurst Field Annex, which is across campus near Bancroft. So you can find me there, Building B. And then, as you were all introduced last time to the 4 GSIs, graduate student instructors, they're sitting amongst you here in the audience, and here are their names and their email addresses. You should feel free to email any of them. There isn't ownership, so to speak, between the graduate student instructors and you all. So feel free to email whichever one, or me. If those of you who have already emailed me this semester, you know that I often respond within a few minutes. And the GSIs will be the same. They're all fantastic. Really, we are very lucky to have the 4 GSIs that we have. They'll answer any of your questions. And then optional each week are 2 opportunities to meet with us, discussion sections for 1 hour. You're all signed up for one. They're optional. You can go if you want. They're an opportunity to get help with concepts that came up in lecture. Some new ideas will be presented in discussion section. You can get help on homework. And then in addition, we have something called the Astronomy Learning Center, which is a place where you can go and other students in this class will be there. And you can talk to them, meet them, and work on your homework together. It's totally fair to chat with each other about homework problems or anything else, and then do the homework, of course, separately without copying what the other person did. But you can collaborate, chit-chat, maybe even argue about the right answer to a homework problem, and then do it on your own. The lectures, as you all know, they're Tuesdays and Thursdays. I issued a warning last time. I'll remind you again that there's some remarkable and new research that shows that students who are in lecture with their cell phones out and their laptops out, if you're getting email and you're getting texts or you're surfing the web, I promise you you're not able to spend the kind of attention you need to really understand the lectures. And that's probably true for all of your classes. So I caution you against being online in class. My lectures, the slides are all located in Mastering Astronomy. You can get the PDF files there. And even though I'm not sure they're in yet, there will be audio recordings with the real-time PowerPoint presentation that I'm giving online in these 4 locations that you see here. Has anyone found them yet? I didn't find them. You did? Okay, so a few people have. So maybe they just now came online. I checked a couple days ago. So you can actually hear my lecture with the associated slides and movies, as well as look at the PDF files. What this means is something really, I think, fantastic. You shouldn't feel compelled to take notes. It's okay to take notes. Oh dear. Let's see, now I'm gonna have to do something about this. I don't know what. You shouldn't feel compelled to take notes. You can just listen to me, watch the lecture, watch the slides, and that's good enough. So I don't think you need to take notes. Research shows that if you have a piece of paper in front of you and a pen or a pencil, and you write down some ideas that maybe don't appear on the slides or something that you're not sure about, writing things down helps your memory. It helps you understand what the lecturer has said. So the actual act of writing and taking notes with your hand reinforces the memory in your brain. So it's actually a good thing to take notes, but I don't think it's critical. It's not necessary. Most of what you need to know is just going to be sitting in the lecture, and it's in the book. and you can get it all online or in the book. Okay, now let me talk about the solar system. I'll do a very quick review of the last lecture, and then we'll launch into some new concepts about the scale, the sizes, a basic structure of our solar system. So let me remind you of the basic ingredients of our solar system. The sun is by far the most massive member of our solar system. Oddly, we won't talk about the sun until about midway through the semester, around October 21st. Meanwhile, there are 8 major planets in the solar system, in order from the sun. All of you now have it memorized: Mercury, Venus, Earth, Mars, and then the giant planets Jupiter, Saturn, Uranus, Neptune, demoted, puny little runts, and then, okay, Pluto, and then asteroids and comets. And we'll be talking about all of those, as well as moons that orbit the planets, why the moons are as different as they are, rings that exist around planets, how those rings came to be, what they're made of, and what their fate is. The structure of the solar system you all know from elementary school, but to remind you, the sun is surrounded by 4 small planets in relatively small orbits. Mercury, Venus, Earth, and Mars. They're rocky planets, very little atmospheric gases. We'll talk a lot about them in detail during the semester. They're close in. You can take all 4 inner terrestrial planets, as they're called, and put them into that little red ring there, and then the rest of the solar system is shown to scale: Jupiter, Saturn, Uranus, and Neptune, and there's Pluto again. So the solar system, in effect, consists of 2 domains: an inner terrestrial domain with 4 small rocky planets in small circular orbits, and an outer domain with the 4 gas giant planets rich in hydrogen and helium gas. Remember the 2 simplest elements on the periodic table to your left, hydrogen and helium. Those gases comprise most of the big planets, Jupiter, Saturn, Uranus, and Neptune, and they too reside in circular orbits. And by the way, a topic we'll refer to later, all of the planets go around the sun in the same direction, and they all reside in roughly the same flattened plane, like a sheet of paper slicing through the solar system. And this is a major clue about the formation of our solar system. All of the planets, it can't be a coincidence, orbit the sun in the same direction, counterclockwise, as seen from above. Keep that in mind, counterclockwise, this away. And they all reside in more or less the same flattened plane. Surely those 2 factors, the fact that they go around the sun in the same direction and the fact that the planets lie in the same plane, must be a fundamental clue about how our solar system formed, how it was born, what the processes were that led to the solar system that we live in, that we love so much. It's something about that formation process led to the current architecture. Our solar system, that we're going to spend much of the semester studying and describing, learning about the nature of the inhabitants of our solar system, is just one planetary system with a star in the center, our sun, and planets going around it. It's just one planetary system of billions, hundreds of billions, within our Milky Way galaxy of stars. 200 billion stars. This is an actual photograph of our Milky Way galaxy from the inside. There's a center, and there's a flattened, ooh, that reminds me of our solar system, a flattened distribution of stars. Yeah, it looks like a line, but that's because we're seeing our entire Milky Way galaxy edge on. We live within the pancake, the DVD of our Milky Way galaxy. So as seen from within it, our galaxy just looks like a flattened disk, like looking at a DVD edge on. But then there's a bulge in the center, downtown for the Milky Way galaxy. And this whole Milky Way galaxy contains 200 billion stars. All of them are more or less like our sun, plus or minus. Some of the stars are smaller than the sun. Some of the stars are 5, 10, or even 100 times larger than the sun. And the sun is somewhere in the middle. And we live not downtown in the Milky Way galaxy, but out in the boonies, in the suburbs. There we are, sun and the 8 major planets. Okay. Now, our Milky Way galaxy is worthy of study in itself. We won't be talking about our galaxy very much this semester, but here's an artist's rendering, a very accurate one. There's our galaxy now seen face on, so you don't see it edge on, but face on. There's the bulge. The sun and the solar system reside some 28,000 light years from the center of the galaxy. I'll be telling you what a light year is in about 10 minutes. But our sun and the solar system orbit the galaxy, orbit the center of the galaxy. So our sun is just one star of many. Why does our sun orbit the center of our galaxy? Because our sun and the solar system are held to the rest of the galaxy by gravity. Gravity is yanking on our sun, yanking on the Earth, yanking on all the other planets, pulling our solar system around in a big arc around the galaxy. It takes about 230 million years for us to complete one orbit around the center of the galaxy. Of course, just to back up, it takes our Earth just 1 year to go around the sun. But meanwhile, the sun and the Earth, taking 1 year to go around each other, that whole structure and the solar system goes around the center of the galaxy in about 230 million years. Yeah. How would it be impacted? Oh, that's a good question. Not much, actually. If our solar system were closer in, we would see the bulge of our galaxy looming even brighter, even larger. We'd incur a few more supernova explosions that might cause some mutations. Maybe the mutation rate would go up. For you biologists who feel that Darwinian evolution is too slow for you, we would be evolving faster. And meanwhile, the other thing about our galaxy is that our sun is just one of course, 200 billion stars. And if you look locally in a little region around our sun, the solar neighborhood, you will see our sun surrounded by other stars, and they are all moving in peculiar velocities. They're moving with motions that are random relative to each other, sort of like bugs on a hot summer day fluttering around, each moving in different directions. The stars near our sun are each moving in random directions with random velocities. I can tell you the typical speed is something like 20 miles per second. Our sun is moving about 20 miles per second relative to the other stars in some random direction. And so you see our sun is really just one of the other stars, and most of them have planets going around them too, as we'll discuss later. Yeah. Why does the galaxy rotate clockwise? You mean clockwise or counterclockwise? I don't really know which way the galaxy rotates, to be honest with you. I'll just give you a quick answer. Whenever you ask a question, why is it that the planets go counterclockwise? Or why is it that the galaxy rotates in some direction or another about the center? The answer is way back in the formation of the solar system, of the galaxy, the atoms of which the stars and the planets are made, had some net rotation to them. And that rotation, sometimes called angular momentum, stays with the object forever. It conserves angular momentum, and we'll talk about that in about 3 weeks. So once an object starts spinning in a certain direction, it keeps spinning. Yeah.
What's in the center of the galaxy?
The question is, what's in the center of the Milky Way galaxy? And the answer is, there's a supermassive black hole with about 1 million times the mass of our sun. Yeah.
And you can confirm or deny, but from what it seems like, there is a high possibility for extraterrestrial life because there's so many stars.
She's asking whether there's a high probability of extraterrestrial life, and I will deny having an answer to it, because NASA told me I couldn't say anything. The second to last week of the semester will be all about the prospects of life elsewhere in the universe. So we will get there. Okay, now our Milky Way galaxy, you see it as a big pinwheel, is just one of hundreds of billions of galaxies, many of which are spiral arm galaxies. Let me show you a few examples of pictures of other spiral arm galaxies taken with powerful telescopes. Here are 4 examples of spiral galaxies. They are gorgeous, beautiful colors, beautiful spiral arms, hundreds of billions of stars, different shapes. Some of the spiral galaxies have a bar through the center. Most of them have a bulge of high collection, densely packed stars near the center. Some of them have clumps, some of them have colors, some of them less so. The study of galaxies is worthy of a whole course in and of itself. We won't be talking too much about galaxies. They are, of course, not only outside our solar system, but those galaxies are outside our own galaxy, the Milky Way. So we won't spend too much time on them, but I knew you'd want to see the context of other galaxies. Some of them, by the way, are not spiral armed. Some of them are sort of amorphous blobs, like a ball of cotton. Here are 3 examples. Elliptical galaxies. There's one, there's another, there's another. They come in different shapes, sizes, colors, and you might ask, why would galaxies have different colors? We'll talk about that a little bit later. But you can see that there's a second type of galaxy, the elliptical galaxies. They look more like cotton balls. They contain hundreds of billions of stars, just like the spiral galaxies do. And moreover, there are some weirdo galaxies, galaxies with wacky shapes, so wacky we can't even characterize them. They're called irregular galaxies, and you can see how weird they look. Yeah.
Do all galaxies rotate?
Do all galaxies rotate? Essentially, yes. They all have some rotation, some faster than others. In addition, galaxies in the universe, these giant collections of hundreds of billions of stars, themselves clump together in clusters of galaxies. And here's an example of a sketch of the nearest galaxies to us. There's the Milky Way. We have sextans, large Magellanic Cloud, small Magellanic Cloud, Sculptor, Fornax, Carina, and so on. This is about 100,000 light years. Our nearest giant galaxy is called the Andromeda Galaxy. This is an actual picture of it. Andromeda, some of the other nearby galaxies. We live in a group of galaxies, a local group of galaxies. And it turns out that our local group of galaxies is clumped with other groups of galaxies in a giant cluster of galaxies. Here they are. There's our local group, 100 million light years across. And our local group of galaxies is dwarfed by the entire cluster of galaxies that we live in. There are their names. We live, of course, in our local group of galaxies, but all of these are the names of other groups of galaxies. And so galaxies come clumped, and there are even superclusters of galaxies. And our universe as a whole consists of hundreds of billions of galaxies. I mentioned last time that the Hubble Space Telescope took a long exposure of a blank part of the sky, dark, pitch black, and instead of the picture coming out pitch black, it came out with thousands of galaxies, and you see some of it here. When you take that postage stamp in the night sky and you extrapolate to the whole sky, you learn that our observable universe, the universe that we could detect with the most powerful telescopes, has hundreds of billions of galaxies. Now at this point I should warn you that, let me see if I have an example here. We're going to need these 4 colored pieces of paper, so if you don't have your 4 colored pieces of paper out, you should get it. And if you don't have one, you should bring it to class every day, every time we have lecture. You have a few extras. So if you don't have one, maybe raise your, we may not have as many as we need, but we'll pass out as many as we've got. You want to pass these back? While you're collecting the 4 colored pieces of paper, the volleyball team needs one right back there. What happened? Well, let's keep going because we have a lot to cover. While you're getting your pieces of paper, let me tell you a little bit about how we use numbers in astronomy and in science in general. There are in science large numbers and small numbers, so large and small that we normally use exponential notation. And I'll remind you what exponential notation is. I think all of you learned about it, but let me give you a refresher course. When you have a large number like 1,000, it's convenient to write it as 10 to the 3. A million, instead of writing 6 zeros, which is boring, you just write 10 to the 6. A billion, instead of 9 zeros, you write 10 to the 9. And a trillion, instead of writing 12 zeros, 10 to the 12. You can go towards smaller numbers as well. 10 to the minus 3 is 1 divided by 1,000, a thousandth, in other words. 10 to the minus 6 is a millionth, 10 to the minus 9 is a billionth, 10 to the minus 12 is a trillionth. I think I see a couple of hands back there. Let me give you an example, and then we're going to have a quiz. If you want to multiply 1,000 by a million, you might wonder, what's 1,000 times a million? Well, it's easy to do in exponential notation. You take 10 to the 3 for 1,000, 10 to the 6 for a million, and the rule is, when you're multiplying 2 numbers with exponential notation, you add the exponents. The number of zeros adds up, and so 1,000 times a million is simply 10 to the 9. Very convenient. And in general, obviously, 10 to the capital N times 10 to the capital M is equal to 10 to the sum of the 2. Okay? Now a quiz. How many stars are in the observable universe? I'll give you 10 seconds to think about it. How many stars are in our observable universe? You have to kind of think about these questions. It's not easy. All right, hold up your answers. That's beautiful. I'll tell you what colors I see. Do you know the precise meaning of the word rainbow? I see blues, reds, yellows, and greens in equal numbers. Blues, reds, yellows, and greens in equal numbers. I'll tell you what I'm going to do. I'll make you a deal. Even the volleyball team disagrees with itself. I'll tell you what I'm going to do. I'm going to give you 1 minute to think this more carefully, and I would like you to talk to somebody sitting next to you. If you know who's sitting next to you, talk to them. If you're sort of by yourself, go over and talk to the other two people. Everybody should be talking to somebody. You have to talk to the people behind you. If you're kind of by yourself, talk to somebody. I want to give you 1 minute, and I want to see a change in your answer after a minute. Go ahead and talk about it. Change your answer? All right. You want to hold up your answers again? Ah, I see a change of color. That's a horse of a different color. There are A's, B's, C's, and D's. There's our cluster of C's over there. Lots of different colors over here. Let me tell you how I do the problem. The number of stars in the galaxy is about 200 billion. Exponential notation, 200 times 10 to the 9 is 2 times 10 to the 11. The number of galaxies in the observable universe, remember, is something like 100 billion, I just mentioned. If you multiply these two numbers, stars per galaxy and the number of galaxies, you have 10 to the 11 times 10 to the 11 with a factor of 2, which is 10 to the 22. So it's a good example where, by the way, many of you did change your answer, and it looked like most of you that changed your answer changed for the better. But you might want to think a little bit about how to work through a problem, and if you disagree with your neighbor, how do you decide who's right? How do you talk it through to get to a better answer? And also, by the way, using exponential notation. Yeah.
So it's a known fact that in each galaxy there's about 200 billion.
That's right. It's a known fact that each galaxy, roughly speaking, has about 100 billion stars. The Andromeda galaxy has 200 billion stars. Yep. I mean, some galaxies are smaller than others, some are bigger than others. Let's talk about economics. You all owe a lot of money. You were born owing a lot of money. You probably will die owing a lot of money. But meanwhile, you're going to live a life owing a lot of money. And here's how much. In 2014, the debt was a lot. These are numbers in the trillions of dollars that the United States owes. And of course, this leads to a question. $1 trillion, that sounds like an astronomical number. 10 to the 11 stars in the Milky Way galaxy, you normally think of that as sort of an astronomical number. But I think the economists have blown us away. We should really be calling them economical numbers. And so you can see that if you want to be a business person or a doctor, or if you want to go into environmental science, or if you want to study human beings in any way, you're going to be dealing with large numbers, large amounts of dollars, and so on. Here's how much you owe as a country: $17.7 trillion. I just got this off the web before class. $17.7 trillion, and that leads to a question. That's a lot of money. How much do you personally owe? Well, it's the total debt of the country divided by the number of people in the United States. The number of people in the United States is about 320 million. So if you divide the debt by how many people, you find out how much each one of us owes on average, and the answer is 17.7 trillion divided by 3.2 times 10 to the 8, that's 320 million. If you want to do the division in your head, you can. 17 divided by 3 is about 5. 10 to the 12 divided by 10 to the 8 is 10 to the 4, doing the difference. Here it is spelled out. And the answer is 5.5 times 10 to the 4. What does that mean in real terms? Put 4 zeros move the decimal over 4 places, $55,000. All of you thought that the debt you have taken on to come to UC Berkeley is a big debt. You actually owe a whole lot more even before you walked on campus. So go to work. Start making a living here. All right, exponential numbers are used all over the map. You already know this. The radius of our Milky Way galaxy is ginormous, but we write it as 6 times 10 to the 18 meters. The radius of a hydrogen atom, 0.5 times 10 to the minus 10 meters. The time to vibrate an oxygen molecule, 10 to the minus 14 seconds, very fast. And the age of the universe, 4.3 times 10 to the 17 seconds. That's how old our universe is, which, by the way, is 13.8 billion years. So exponential notation is used all the time. And in addition, we always have to use units for any measurement in science. All of you know about this, but let me remind you. The metric system is what everybody uses now when you're doing science, certainly, or most other activities as well. Sometimes it's called the SI system, or if you live in France, it's the Système International. And it has certain units. A meter is about a yard. A football field is 100 meters long. You run the 100-meter dash in the Olympics. Mass is judged by kilograms, which is about 2.2 pounds. A second is a second, that's the same. And you can derive other units when you're using the metric system. For example, a kilometer is 10 to the 3 meters. Kilo means 10 to the 3. A gram is 10 to the minus 3 kilograms. So a kilogram is 10 to the 3. And then a millisecond is a thousandth of a second, and there's microseconds, 10 to the minus 6 seconds, and nanoseconds is 10 to the minus 9 seconds, and a picosecond, I think, is 10 to the minus 12 seconds, and so on. Units are very important. If you make a mistake with units, you'll get the whole problem wrong. And NASA did it. They made the mistake. They sent up a spacecraft to Mars called the Mars Climate Orbiter. There it is. It went up. It launched successfully in 1998. It went into orbit around Mars in 1999, and it was supposed to land on Mars, but they didn't do the conversion from meters to feet properly, and so it crashed on Mars. We don't know because no one ever saw it happen, but we lost communication, and the spacecraft obviously shattered into little bits because somebody made an error in units. Some engineer at NASA didn't convert from the units like inches and feet into meters and kilometers. And so we lost a $1 billion spacecraft because of unit error. You can read about it on the web. It's quite embarrassing. And this kind of thing can happen all the time. I'm going to keep going. Okay, let me talk about speed of light. We've talked about a light year already. Let me tell you what the heck it is. Speed of light. How fast is light? Pretty darn fast. You all know it's 186,000 miles per second. In metric units, SI units, it's 300 million meters per second. 3 times 10 to the 8 meters in a second. See my laser pointer? When I turn it on and shine it on the wall over there, when I press the button, the beam of light travels at 3 times 10 to the 8 meters, or 300,000 kilometers each second. So when I press this button, the beam seems to hit the wall instantly. That's how fast light is. You can write it as 300,000 kilometers a second. You can do various calculations. How far does light go in a year? Well, in a year, light traveling at 300 million meters per second goes a really, really long way. And the answer is it goes 1 light year by definition. Light goes a light year in a year, or in other words, 9 trillion kilometers, which is 6 trillion miles. In 1 year, light travels 6 trillion miles. A light year is a unit of distance, not a unit of time or speed, but distance. It's the distance light travels in 1 year. So that's what a light year is. How about a light second? How far is a light second? Well, it's how far light travels in 1 second. And you already know the answer because light goes 3 times 10 to the 8 meters per second. So a light second is, of course, 3 times 10 to the 8 meters. Very simple. Or 3 times 10 to the 5 kilometers, 300,000 kilometers. Okay? That's speed of light. Here's a question. How long does it take sunlight to reach the Earth? When a photon of light is emitted by the sun, how long does it take that light? Yeah, some of you have it memorized. And the answer is you can calculate it, even if you don't have it memorized. You can calculate it because you can use a formula that I hope all of you know, and I'll remind you of it. The most powerful formula probably in all of science is that distance is equal to the speed of something times the time it travels. Distance equals velocity times time. And so we can solve for the time in this algebra equation, divide both sides of the equation by velocity to just isolate the time, which is what we want, the time. So if you do that, distance equals velocity times time, divide both sides by velocity, you get that the distance from the Earth to the Sun, which by the way is 1.5 times 10 to the 11 meters, that's by the way called an astronomical unit. This is an aside, but an important one. The distance from the Earth to the Sun, 1.5 times 10 to the 11 meters. Don't memorize that number. Even I don't have it memorized. But we will call it all semester long 1 astronomical unit. Earth-Sun distance, 1 AU for short. It's the scale of our solar system, the size scale, 1 AU. The speed of light is 3 times 10 to the 8 meters a second. So now you have a distance and a speed. Solve for time. That's right here. All of you should remind yourself of basic algebra where you divide both sides of the equation by velocity. And now time is distance divided by velocity. There's the distance from the Earth to the sun. There's the velocity of light, the speed of light in the denominator. How do you divide these two? Well, remember there's an exponential notation. 10 to the 11 divided by 10 to the 8 is 10 to the 3, doing the subtraction. That's 10 to the 3. And then 1.5 divided by 3 is a half. So it's a half times 10 to the 3 seconds. 500 seconds is about 8 minutes. So, yeah. So the time it takes light to go from the sun to the Earth, about 8 minutes. And that leads to a quiz question. What about the time it takes sunlight to reach Mars? How long does it take a radio wave, and by the way, radio waves are light of long wavelength. How long does it take a radio wave to go, well, let's do it a little differently. How long does it take radio waves to go from the Earth, where we have our control systems for NASA, how long does it take a radio wave to go from the Earth to Mars? Give it a little bit of thought. I'll give you 10 seconds, and then I'll ask for your answers. All right, go ahead and show me your answers. I see greens. I see very tall greens. I see very confident greens. I see some not so sure yellows, a blue here, there, and a couple of reds. Well, this is not an easy problem. You have to think about the picture of the solar system I showed you. Sun, Mercury, Venus, Earth, Mars. The distance between Earth and Mars is a fraction of the distance from the sun to the Earth, 1 AU. So if it took 8 minutes for sunlight to reach the Earth, the time it takes light to go from the Earth a little bit farther to Mars is probably less than 8 minutes. If Mars is on the same side of the sun as the Earth is, which I didn't say. You thought that I was an honest professor, but I'm not. Earth to Mars, well, it could be 55 million kilometers, but if Mars is on the other side, it's a lot farther. If it's on the near side, it only takes 3 minutes, so those of you who put B would have been more or less right. But if Mars is on the other side of the sun during its orbit, then it's 400 million kilometers away, and obviously it's going to take more than 8 minutes, something more like, say, 10 minutes, actually 22 minutes. So actually there were 2 right answers, B and C. And notice that neither answer is exactly right, because who cares? It depends on where Mars is around in the orbit. And you know, we're not trying to get the answer to the nearest nanosecond. We just want to know roughly, is it minutes, hours, days, centuries, roughly? And the answer is it's a few minutes. So when the NASA engineers are commanding the rovers on Mars, they have to send the signal to the rover several minutes before the rover will even receive the message. Okay, now I want to build a model of the solar system. What is a model? Well, in science, we never understand the details of the phenomenon precisely. A cell in biology has a cell membrane, there's a nucleus, there's mitochondria, there's this DNA stuff that's inside. We have a concept of the atomic and molecular makeup, but we don't know exactly where every single atom is perfectly. We have a model, a theory, a notion about how a cell works. And the same is true in chemistry, physics, astronomy, geology. You build a model, and usually the models are a scaled down or a scaled up version of the real thing. So I want to build a scaled down model of the solar system. Solar system is huge. Let's shrink the solar system. And I propose to shrink it by a factor of 10 billion. Let's shrink the solar system by a factor of 10 billion. 1 billion is 10 to the 9. 10 billion is 10 to the 10. So let's shrink the whole solar system down. It turns out when you shrink the sun itself with its diameter of 14 times 10 to the 10 centimeters, that's the diameter of the sun, if you shrink this by 10 to the 10, you divide out the 10 to the 10, and the whole sun shrinks down to the size of a grapefruit. And it just so happens I brought one. Just a coincidence. Here's our scaled down solar system. If the solar system could be shrunk by 10 to the 10, this is how big the sun would be. And now you could ask, with this as the sun in our model solar system, how big would the Earth be? Well, the Earth is 13,000 kilometers across in diameter. Divide by 10 to the 10, and you get 0.13 centimeters, a tenth of a centimeter. Well, I don't have a little bead as small as a tenth of a centimeter because you wouldn't be able to see it. So I hope you don't mind if I brought an enlarged Earth. This is the Earth, huge on this scale. The Earth should be the size of a little fleck of a grain of sand on the beach. And so here we have the sun and the Earth roughly to scale. Even have the colors right. And now you might ask, well, how big are the other planets? Jupiter? Oh, that's exciting. You can see these scaled down. Jupiter would be 1.5 centimeters across. What about 1 AU? 1 AU is this large distance, 1.5 times 10 to the 8 kilometers. When you scale that down by 10 to the 10, how big does it come out to be? You want to think about it for a moment? Let me give you 10 or 20 seconds. What's 1 AU in our, how far apart should I place the Earth relative to the sun? How far should they be from each other? Give it a little thought. The real distance is 1.5 times 10 to the 8 kilometers. Divide by 10 to the 10. So before you show me your answers, let me tell you, this problem is too hard for me to do. And I'll tell you why, and then I'll do it anyway. It's too hard because if I take 10 to the 8 and I divide by 10 to the 10, I get 10 to the minus 2, and that starts confusing me. 10 to the minus 2 kilometers, I don't know what that is exactly. So I cheat. 10 to the 8 kilometers, let's convert to meters so we get up to a number bigger than 10 to the 10. 10 to the 8 kilometers is how many meters? Well, 10 to the 11 meters. Why do I say 10 to the 11? Because there's 1,000 meters in 1 kilometer, 10 to the 3 meters. So if I convert this to meters right away, I get 10 to the 11 meters. And now I have 1.5 times 10 to the 11 meters. I need to divide by 10 to the 10. So the 10 to the 11 gets cut down to 10 to the 1, which is 10. So 1.5 times 10 is 15. And so I won't even ask for a show of papers, but there is 15 meters. In other words, 15 centimeters. 15 meters. So here's the sun. I'll put it right here. There's our model sun. I have to take this Earth and move it 15 meters away. A meter is about one stride, so I'll walk this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This guy is going to hold the Earth. Take good care of that thing. All of humanity that ever lived, ever will live, is on that little Earth right there. All of the civilizations, all of the illicit love affairs, they occurred on that little ball. You still got it? Okay. This shows you the scale of the solar system. Look at the grapefruit, and now look at the Earth way over there. That's the scale of our model solar system. You can picture Mercury and Venus at 1/3 and 2/3 of the distances in between. And now we can ask, well, where should the rest of the planets go? And of course, if the grapefruit is 14 centimeters across, Mercury, Venus, Earth will be 6 meters, 10 meters. There's the 15 meters again. I walked up 15 rows. Do you still have the Earth? Okay, good. What about the rest of the solar system? Real quickly, you scale it up. Mars, 22 meters. Jupiter, 70, a football field away. Saturn, 1.5 football fields away, and so on. Here's where they would all be. There's the original sun. Let's scale the sun down by 10 to the 10. There's the grapefruit. Don't laugh, this is science. There's Pimentel. There's the grapefruit. And that red circle is where he's holding the Earth. That's the orbit of the Earth, 15 meters away in the outskirts of Pimentel, right within the hall. Where would Mars be? Well, let's get scale. Here's Memorial Stadium, 100 meters across for a touchdown. And there's where Jupiter would be at 5 AUs. Saturn at about 10 AUs. Uranus would go out to Bancroft Avenue almost. There's Bancroft. So Uranus would be there. And Neptune would be out here at Dwight Way or so near Residence Hall Unit 2. Pluto, of course, even farther out. And so there you see a scaled solar system. We could spend the next 20 minutes walking around campus, dropping off little planets along the way. When we finally get to Dwight Way out there at Unit 2, we'd have given away all the planets. And you can imagine signposts on campus, a scaled solar system. Notice the amount of space, empty space there is between the planets. It's amazing how much space. Now, with all of that distance in our scaled down universe, with the sun shrunk to a grapefruit, the Earth, how's it doing? Okay. And the Earth 15 meters away in our scaled universe, how far away on this scale is the nearest star, Alpha Centauri? How far away should it be? Well, I can tell you Alpha Centauri is 4 light years away. When you see Alpha Centauri, you're seeing the light that left that star 4 years ago, and it just now arrived. On our scaled solar system, you could work it out. If you put Berkeley and San Francisco over here, the nearest grapefruit, i.e. Alpha Centauri, is in Washington, D.C. So there's just empty outer space between Berkeley and Washington, D.C. There's nothing in between. Our whole solar system is contained on campus, and then there's nothing until you get to Washington, D.C. That's a scaled universe. And then the next star is another 4 or 5 light years away, and so on. You get an idea of how enormous the universe is. Now, I want to show a little movie. It's about 6 minutes that will give you a sense of everything we've described so far. I love this movie, and I hope that you like it too. Movie. And I'll just finish with one more slide that I think is relevant to everything we've talked about. You may have caught me when I said that when you look at Alpha Centauri, 4 light years away, the light traveled here taking 4 years by definition of a light year. So when you look up into the stars at night, like you might do this evening or during the semester, you're seeing the stars, the planets, even the galaxies, as they were when the light left those objects, however many light seconds, light minutes, light years away they happen to be. So for example, it takes 8 minutes for light to go from the sun to the earth. When you see sunlight, when you see the sun up, you're seeing where the sun was 8 minutes ago. And when you look at a star that's 8 light years away, you're seeing what the star looked like 8 years ago. The Orion Nebula that we'll see later in the semester is 1,500 light years away. When you see it in a telescope, you're seeing what that nebula looked like 1,500 years ago. You have no idea what it looks like now. All you know is what it looked like then. And the farthest galaxies, as shown in this cartoon, the farthest galaxies are in fact millions or even billions of light years away. And so when you look at a nearby galaxy, you're seeing what the galaxy looked like when it emitted the light billions of years ago. The galaxy may be utterly different now, but you're seeing it as it was. And so when you look up into the night sky, it's literally a time machine with your naked eye. You're seeing what the universe was like at some point in the past. So I'm going to stop there, and the next lecture we're going to start talking about the phases of the moon and the seasons.